And okay, we're live. Which question did you have?
For example 3 in Euler's method.
Okay. So we were given an initial y value, an initial x value, and a derivative at that point. So this is the same idea as what we were doing earlier, only instead of giving you an equation for the derivative, I'm giving you the value after you plug everything in. So this is actually easier. What's our formula for Euler's method?
Y new is equal to y previous plus change of x times dy over dx.
Okay, change in x times our derivative, which is delta y over delta x. Okay. So
And
what should happen next?
I was gonna ask, is y previous fx?
Yes.
Okay.
So your y value is your output. So in function notation, that'll be whatever your function's variable is of whatever your input is. Same here. So this is the derivative function, f prime, and then I'm plugging in x into that, and I'll get an output. But if I was going to graph the derivative, that would still end up being on the y-axis. Original function derivative. Okay, so taking a look at this, if I want my new y value, here at x equals 2.8. So I'm solving for f of 2.8. Rewrite this kind of at an angle. F of 2.8. Okay. Is my previous y value, which should be what?
So 2 plus negative 0.2 times 0.4.
Perfect.
Which is 1.92.
Okay, I think you got it. So if that's f of 2.8, then we just keep repeating. So this is 1.92. And we can go up and do the next one. I'm going to see if we have anybody else here. Okay, I did have Alien just jumped in. Okay, Kyle, what comes next?
We're trying to find the f of 2.6.
Okay, so my new y value is equal to my previous y value, which should be what?
1.92.
Okay, that's f of 2.8, which is 1.92. Okay, plus
negative 0.2.
Okay, from 2.8 to 2.6, I went down by 0.2. Perfect.
So we changed the derivative, so it's going to be 0.7 instead.
Perfect, because our derivative is based on the previous point. So my previous derivative was 0.7. Yeah, you got this. So that leaves us with 1.92 minus 0.14, right?
Yes. F of 2.6.
Oh, I'm sorry, say again?
Oh, nothing. Sorry.
Okay. So I got 1.78, right?
Yes.
Okay. Cool. Any questions on that one? You pretty much walked me through it, so I think you knew how to do it. You just wanted me to confirm, maybe. All right.
Like the one that I had a problem with was the example 1b, because I don't know how it's phrased differently.
Solve the differential equation with the initial condition and use your solution to find y of 0.8. So in this case, they'll want us to integrate. So part A is using Euler's method to estimate an integral. Part B, we're actually solving the equation. So if my derivative is x minus 2, then that means my original problem would be the integral of x minus 2, which I'll write out really quick. There we go. So if f prime x is x minus 2, then f of x should be equal to the integral of f prime x in terms of x. So what would that be equal to? What is the integral of x minus 2 in terms of x?
Oh, we're integrating, so it's going to be x squared over 2 minus 2x.
Okay, plus
C.
Plus c. Okay, that plus c is what I'm concerned about, because we were given an initial condition that will allow us to solve for what c is. So if I know that when x is 0, y is 5, when x is 0, f of x is 5, then I can use that and plug it in to solve for c, and we'll get an actual answer for what the real equation was. And then we can use that real equation to solve for what our y value is when x is 0.8. Okay, so here goes. I know that, I think I'm going to run out of space, but I'll zoom in a bit. I was told that, I'm just going to change my notation too, so I match. These are y's, not f's. Sorry. Y prime, y prime. Okay, so when we plug in 0 into our equation for y, we get 5. Therefore, 5 should be equal to our original equation when we plug in x equals 0. So if I plug in x equals 0, that's 0 squared over 2 minus 2 times 0 plus c. Therefore, c is 5. So my original problem for any x value was x squared over 2 minus 2x plus 5. Then I can use this equation, use your solution to find y when x is 0.8. So the actual answer when x was 0.8 would be this. So I've got 0.8, I'm going to do this in fractions, that's easier for me, so that's 8 over 10. So this is 8 over 10 squared divided by 2 minus 2 times 8 over 10 plus 5. Okay, 8 over 10 is the same thing as 4 over 5. 4 squared is 16, divided by 2 is 8. So I've got 8 over 5. Minus my 2 and my 10 can cancel, so this is also 8 over 5 plus 5. Therefore, y at 0.8 is equal to 5. Okay, then they wanted you to compare. I think they wanted you to compare, did they? No, they didn't actually ask you to compare, but we could compare since this is what the actual value was, and Euler's method is an estimate. If you remember from last class period, what we're really doing here with Euler's method is we're taking one point and the slope at that point. So I know the slope of the original function was this. And then extending that out for some change in x to make an estimate for another point. So I'm going to make estimates here in green. With our slope of the line here in blue, for instance. Okay, but let's say the actual function here in black was something like this. So I took the slope that was actually at that real point and extended that out to make an estimate for the next point. And so as we went, we had error here in red, where our point was a little bit wrong. Our estimate using Euler's method was a little bit wrong. Because we know how to integrate and we know what the initial condition was, we could integrate and get an exact answer for this problem. So that allows us to check how bad was Euler's method for this particular problem. And maybe we could use that as a guide if this was a physics class. For this problem that we know how to integrate, here's how wrong we were. So maybe for this problem that we don't know how to integrate in the same situation, we can expect that we'll have about the same amount of error. Does that make sense?
Yes.
Okay. This was worded a little bit weird. I don't think we've seen this before. We're given a derivative and an initial condition, or if we have, it's been a while. But if you're given a differential equation dy in terms of x, we should be able to integrate that in terms of x to get back to our original y value. Okay.
Are there certain words we need to look out for, like that implies that we need to integrate?
For this one, it wasn't so much words as what they gave you in the math notation. So we had a differential equation, and we were trying to find an original y value. So in order to go from a derivative to an original function, I would need to integrate. If you do want to use words, anytime that you need to solve a differential equation, typically that means you'll have to integrate. So you'll have to get back to the original problem. When you're solving differential equation, you can solve for general solutions, which is what I have here. So this is the general solution. There is more than one function that has this slope of x minus 2, but for any function that has a slope of x minus 2, you would have this form of the original problem where c could be any number you want. But because we know what the original condition was, I know that this point must also be on our original function. Now there's only one particular solution, which is what we solved for here. Particular solution. It's the only one of these infinitely many solutions that also passes through the point 0,5. Does that answer your question?
Yes.
Cool.
Thank you.
Yeah, no problem. All of this is relatively new. I was really pulling this just for the Euler's method, but I'd be okay if everyone had questions on this. That makes sense. Okay, I'm going to jump over to Aileen since she's been waiting. Hello.
Hi. I'm not sure of example 2.
So don't have a particular question or not sure about this last one that we did?
Example 2.
Oh, not sure about example 2. Okay, sorry. All right, example 2. So I've got a differential equation, dy over dx is 2x minus y. Y is 3 when x is 2, so again, we've got a point. I want to use Euler's method with 3 equal steps to approximate y when x is 1.7. Okay, so first, let's talk about what we were given. Oh. Not zooming in. There we go. Okay, so I was given a couple things. First, I've got our derivative. That's why. So we can use that for our slope when we're doing Euler's method. I've got a point. So starting at 2, 3. And we were told we need 3 equal steps to get from x equals 2 to x equals 1.7. So, Aileen, what should my change in x be then?
0.1.
Really close. If it was 0.1, then I would go 2.1, 2.2, 2.3.
Negative 0.1.
Negative 0.1, perfect. Okay, so that's everything we need for Euler's method. My general form for Euler's method is I'm going to have a new y value. It should be equal to my previous y value, plus my change in x times my differential equations. That's my derivative. Okay, so for our start point, what was our previous y value?
Mm. 3.
3. Okay, and our change in x we said was negative 0.1. And my differential equation, I'm going to plug in my previous y and x. So when x is 2 and y is 3, what will my derivative be?
Two.
Okay, so got x is 2, y is 3, so that's 4 minus 3 is 1. Okay, and then this is an estimate for a new y value. After I take a change in x of negative 0.1, what will my new x value be?
2.9.
Close, not 2.9. Oh, I think you're ahead of me, actually. That's my y value. Sorry. What's the x value that we just solved for?
1.9.
1.9, perfect. Sorry about that. Okay, any questions on our first step?
No.
Okay, then I'm just going to keep repeating that process in order to get to x is 1.8 and x is 1.7. I'm going to have you do one more step for me, and then I'll have Niall close us off. So one more step. What's our new x value going to be?
Um, 1.8.
1.8. Let me zoom out a little bit because I'm cutting off our information. Okay, so new x value is 1.8. Okay, then I need my previous y value.
2.9.
Okay, plus change in x.
Negative 0.1.
And multiply by the slope. So my slope is this differential equation, 2x minus y, but I'm going to plug in our previous x and y value. So this will become 2 times my previous x value of 1.9. Minus my previous y value of 2.9. Okay, so I've got that's 3.8 minus 2.9 is 0.9 times the negative 0.1. So I've got negative 0.09, I believe. It's pretty late, so somebody check my addition. I've got 2.81. Does everyone else have the same thing?
Yeah.
Cool. Okay, I'm going to jump over to Niall. Niall, what would my next step be?
I just came in.
Just came in. Okay, so we are doing Euler's method. I've got our given information over here. I've got a differential equation, our start point, and our change in x. So with Euler's method, I've got every new y value is my previous y value plus our change in x times our derivative. Our derivative is based on our differential equation here. So for this first step, in order to get from x equals 2, with 3 equal steps to x equals 1.7, my change in x for every step should be minus 0.1. If I do that 3 times, then I'll get to x equals 1.7. So this first step, I went from my previous y value of 3 plus my change in x of negative 0.1 times my differential equation, 2x minus y, where our previous x and y were 2 and 3, so that's 2 by 2 minus 3 is 1. 1 by our change in x is negative 0.1 is negative 0.1 plus 3 is 2.9. And we did that same thing again. Okay, so now I've got one last step. Will get us to our final x value of 1.7. I need a previous y value. So what was our previous y value?
3.
3 was my original y value. Then I did one step to get to 2.9 for my y value, and another step to get to 2.81. So this previous y value was 2.81. Okay, plus what's our change in x for every step?
Negative 0.1.
Negative 0.1. Okay, again, that was from x equals 2 to x equals 1.7. If I need to use 3 equal steps, I've got a total change in x of negative 0.3. But I'm doing that in 3 steps, so I'll divide that by 3, and that gives me negative 0.1 is the change in x between each step. Okay, then I'm going to multiply by my differential equation, which is 2x minus y. But that's based on my previous point, so that's based on this last point that we did here. So that's 2 times 1.8 minus our y value of 2.81. Okay, I'm going to have you guys check me again. 2 by 1.8 is 3.6 minus 2.81. The 3.6 minus 2.81 is going to give me negative 0.39. Then I've got negative 0.1 times the negative 0.39 is positive 0.039, which is what I'm adding to 2.81 to get our final answer. Apologize again, I'm out of space. This is 2.8. Lost my place, sorry. 2.849. Okay. Okay, somebody check my addition. Are we okay?
3.6 minus 2.81 was 0.79.
0.79. Oh, you're right. Okay. Thank you.
And then it's positive 0.79. So
Okay. So that would be negative then. Okay. So I've got 2.731.
yeah.
Okay, cool. Thank you. Any questions on this one?
I have a question on example 4.
Example 4. Maybe before I do that, does anyone still have a question on example 2?
No.
Oh, okay. All right, example 4. Which part?
Example 4. Can we start from the beginning?
Okay, so I want to prove that my general limit of f of x plus 1 over sine x. Oh, it didn't give us an answer, so just want to find that limit. Okay, so we were not given our original function. However, we were told that y is f of x, and our dy over dx is y squared times 2x plus 2. Okay, I was going to say we should integrate, but I actually don't think they want us to do that. We don't have to, because I know what f of 0 is. So I'm going to cheat a little bit, just to save us some time. Also, we haven't learned how to integrate this yet, so I don't think they want you to do that. If f of 0 is -1, and I go to plug in x equals 0 to take my limit, then I'll have -1 plus 1 over the sine at 0, which is 0, or 0 over 0. So what should I do for my limit? If we try to get the limit and we get 0 over 0, or plus or minus infinity over infinity, then we've got a special rule we need to do. What do we need to do?
Derive.
Derive, yeah. I need to derive the top and the bottom, and that should give us our limit instead. Okay, I'm going to rewrite this so you can see what I just did. So that maybe wasn't very clear. So I took the limit as x approaches 0. So if I take the limit as x approaches 0, limit as x approaches 0 of f of x plus 1 over the sine of x is equal to f of 0 plus 1 over the sine at 0, or -1 plus 1 over 0 is 0 over 0. So that means we can use L'Hospital's rule. Okay, so with L'Hospital's rule, this is going to be the derivative of the top. What's the derivative of f of x plus 1?
Derivative of x.
What's the derivative of f of x? So just in general. Anyone? What could I write for the derivative of f of x plus 1? Okay, I can see Kyle jumping up, but I don't hear anything. So if I derive f of x, I'll get f prime x. If I derive the plus 1, that goes to 0. So this is just f prime x on top. Niall, back to you. What's the derivative of sine?
Should be positive cosine.
Positive cosine? Okay, and now I can plug in 0. This derivative of f is my dy over dx, since y is f of x. So the derivative of y then, y prime, should be f prime, since y and f of x are the same. So that means this top part is really y squared times 2x plus 2, where x is 0 and y is negative 1. The limit as x approaches 0 of f prime, which is y squared times 2x plus 2 over cosine x, or y is negative 1 when x is 0. When x is 0, this will be 2 times 0 plus 2 over the cosine at 0, which is what? What's the cosine at 0?
Cosine of 0 should be
See,
positive 1.
positive 1, right. Okay, I did hear Kyle that time. So negative 1 squared is 1 times the 2 we had on top, over 1 is 2. So this limit is 2. Okay, any questions on my work? Okay, I'm going to skip part B because this one's just Euler's method. So that's the same as the other two examples that we did. For part C, this is really similar to what we did in example 1, part B. We were solving for the differential equation. So I'm going to skip that one too for now, but I'll hold Niall afterwards and go back through example 1 again, since he wasn't here for that one. But they're the same as the other two problems. For part C, when you're finding the particular solution, that does mean that you'll need to integrate. For part B, you'll be using Euler's method.
Mr. Brandon,
Yes.
can for number B, can you help us with setting up the equation, and we can go forward from there.
Can you tell me? So what would your equation setup be?
So we know that y nu is equal to y o plus x dy over dx.
Okay.
So y nu is equal to y involved. So fx. Negative 1.
Yep, your previous 5 value is negative 1. What's your change in x?
2 steps of 1/1/2, so it's 1/4.
1/4. Perfect. And then you've got your differential equation here that you would need to plug in your x and y values. What x value and what y value should you plug in?
The y value would be y is equal to 2 or negative 1.
Okay, y is negative 1, so this is your previous y value. So my previous y value is negative 1, previous x value was 0. Oh, I see. You gave me the whole derivative. So the whole derivative would be 2, yes. Okay, that's everything you need for your first step, and you do the same thing for a second step and get your answer.
Thank you.
I'm a little bit worried about C now that I look at this, though, because I don't think we've learned how to integrate this yet. I may need to go back and cut that. So I've got both x's and y's here, and we can't do that yet. Yeah, I need to cut that, unfortunately. At least I don't think we've done this yet. Did we do separable differential equations in pre-calc? Okay, I am going to do part C for us now, just because we hadn't done that yet. Our differential equation here, dy over dx, was y squared times 2x plus 2. Okay, normally if I wanted to find a particular solution to this differential equation, I would need to integrate in order to get to my original y value. Once you got your original y value, you can plug in your x and y in order to solve for the plus c that you normally have when you integrate. I am going to do the same thing, but we've got a problem because I've got both x's and y's in our problem. So what I'm going to do is I'm going to move all the y's to one side and all the x's to the other, and then we'll integrate that way. Okay, here's what it looks like. I'm going to move all the y's to the left and all the x's to the right. So alien first. If I want to get everything in this problem that has a y value in it and move that to the left side, what would the left side look like?
One over y squared.
1 over y squared, perfect. I've got a dy over here as well, so I'm going to keep that over there. Dy over y squared is equal to what?
Equal to dx times 2x plus 2.
Perfect. 2x plus 2 times dx. Okay, so the problem with our integration is we can only integrate in terms of one variable. But now that I've got two separate problems, one on the left side and one on the right side, I can integrate those two sides separately. So I'm going to integrate 1 over y squared in terms of y. And I'm going to integrate 2x plus 2 in terms of x. And we can just integrate normally. Okay, 1 over y squared, if I wanted to integrate, I'm going to do this a little bit easier by making this a power rule problem. This is now y to the negative 2 power dy. Okay, my right side will stay the same. Okay, I've got less than 1 minute before Zoom kicks us, so once we get kicked, I'm going to post the invite code again. You guys can jump back in. I'm going to pause here because I'm going to get kicked in the middle of the step, I think. Less than 1 minute. Actually, I could just restart manually, I guess. Alright, I'll see you guys in a minute. Okay, Kyle, can you hear me?
Yes.
Awesome. Welcome back. Oh, Aileen, couldn't hear that. Could you try one more time? Oh, there we go. Okay, I heard it a little bit. Niall, can you hear me?
Yeah, I'm good.
Okay, cool. So, back to this one. So really quickly, we threw all our y's on one side, all our x's to the other. Then we integrated. I haven't actually integrated yet. I just rewrote this left side so that I could integrate using power rule instead of having to integrate with this crazy fraction. So if I want to integrate y to the negative 2 power in terms of y, what's going to happen, Kyle?
If we integrate 2x plus 2.
I'll need to integrate both sides, so
Okay, so from the left. So y into
so we're going to integrate with power rule.
it's going to be negative y to the power of negative 3 over 3.
Close. Add 1 to the power or divide by the new power?
Negative 1. So x, negative x.
Okay, so just like that. I'm going to add 1 to the power, so this negative 2 will become negative 1, and then divide by the new power. If I divide by negative 1, that's the same thing as making this negative. Okay, plus c. And then what about the right side?
2x squared over 2.
2x squared over 2 plus
2x plus c.
plus c. Okay, now it's important to note these c's are random constants, but they're not necessarily the same value. So I can't just subtract c from both sides. We don't know what the constant is on the left, and we don't know what the constant is on the right. So right now, if I subtracted c sub 1 minus c sub 2, I would not necessarily get 0. I might, but we haven't proven it yet. Okay, so what I'm going to do is our goal is to solve for y. So I'm going to try to move everything to the opposite side and solve for y. Okay, jumping over to Niall next. Niall, I want to solve for y. What's my first step?
The first step should be I should get rid of power of negative 1.
Okay, so that gives me negative 1 over y plus c1 is equal to 2x squared over 2 plus 2x plus c2. Okay, so these are two separate constants. We don't normally subscript them like this. I'm going to keep doing that just for this first problem, but that's okay. Okay, if I want to get y alone, what do I do next?
Subtract c1 from both sides.
Perfect. So I've got negative 1 over y equals 2x squared over 2 plus 2x plus c2 minus c1. Now this is interesting because c2 minus c1 is a constant minus a constant, which is still a constant. Since these are both constants we don't know, I can just write one constant that we don't know for these two terms. Okay, 2x squared over 2 is x squared plus 2x plus some constant we don't know. Okay, keep going.
Um, is it good if I multiply all the numbers in the equation by y?
Yeah, I would do that. So this is -1 equals x squared plus 2x plus c times y.
Yeah.
And then to get y alone, what would I need to do?
Divide x2 plus 2x plus c.
Perfect.
So it will be y is equal to,
Okay, so y is equal to -1 divided by everything else. X squared plus 2x plus c. Perfect. Okay, so this is our general form. Or general solution. That's not what they asked for. They asked for the particular solution. So what that means is any equation that is in this form with some sort of constant right here, when you derive it, will give you this differential equation, y squared times 2x plus 2. But there's infinitely many answers because c could be any number you want. Only one of those answers, though, will also pass through the point 0, -1. So what I'm going to do is I'm going to plug in 0 and -1 in for x is 0 and y is -1. And that'll allow us to solve for what number c is. And then there'll only be one answer that both has this slope and passes through this point. Okay, does everyone understand what we're doing?
Yes.
Okay, Aileen, you okay?
Yes.
Okay. I'm out of space again, so let me see if I can give myself some more room. There we go. Okay, so for our particular solution, must pass through the point f of 0 equals -1. I'm going to rewrite that f because I don't want this to look like an f prime. Okay. So if I want that to happen, then whenever y is -1, x must be 0. So in that case, we're back to Aileen. We'll need to solve for what c will make it so that this general solution also passes through our point. Okay, so looking at this, what should c be?
1.
1, perfect. If I simplify this, this is -1 over c. Therefore, -c equals -1 or c equals 1. Okay, so our particular solution. Which means the only answer that would have our general form for the slope equals y squared times 2x plus 2 and passes through the point 0, -1 is this. I'm going to take our general solution here and plug in c equals 1. So y is equal to -1 over x squared plus 2x plus c, which is 1. Okay, that was a little bit more advanced than what I was hoping for. And I didn't realize that at first. So I'm okay with giving you an equation where we need to integrate in order to find a particular solution. But I had not taught you guys how to solve if there was both y's and x's in your equation yet. I don't think we'd done separable differential equations yet. So that's my bad. I'll send out a message saying everyone can skip C for now, and then I'll probably go through this again at the start of next class. Any questions on what we did for C though? Okay, again, the idea here is the same. With Euler's method, you made an estimate. So you knew what the slope was at any point, and you knew what the initial condition was. So just like last time, without knowing this black line, but knowing what the slope of the black line is, and knowing what the first point is, you can take that point and that slope and go some change in x to get an estimate for a y value here in green. And then take the actual slope again of the black line from that point, carry that over to get another estimate for a new estimate here at this second green point. If I was actually going to graph the real problem here in black, you can see that we do have some red error here. So Euler's method is not exact. However, the closer together your change in x is, the more exact it will be. And with computers, this becomes more and more relevant to problems that we can't integrate directly. Okay, that's everything for Euler's method. Any other questions on the homework?
Is there a submission tab on course sites, or can we send it through WeChat?
I will allow you to submit through WeChat. There should be a submission tab up on course sites though. I'll load up really quick and double check, but I'm pretty sure I made it available. Okay, any other questions while I'm doing this? Oh, okay. I'll tell you what, I'll double check for that link off screen afterwards. Since we've got about 10 minutes left and I still want to run Niall through the stuff you missed. If I forget and you don't see it, let me know and I can make sure that it becomes available for you guys, if it's not already.
Okay. Thank you.
No problem. Thank you so much for coming.
Good night.
You too. Good night.
Bye.
Bye.
I have to stay, right?
If you don't feel like you need to stay, you can go. If you want to stay, I can walk you through the stuff you missed.
Okay.
Okay. Unfortunately, there is a step on example 3, part C. Example 4, part C.
Wait, what was the schedule for AV class again? It's like, I'm likely to join if I have a time.
You mean what block is it?
I mean, like, for the during the summer vacation when we are having a Zoom call.
Oh, so for Calculus BC, we're doing Saturdays at 9 p.m., I believe now. And then for Calculus AB, it's Mondays at 8 p.m. The content is mostly the same right now, because we're still doing limits. Eventually, it will diverge. We've had a couple extra things in the Calculus BC class that we haven't had in AB, but last week was identical.
Oh. Oh. Does AB students also practice like AP questions?
Yes.
No. Can I join?
Yeah, so feel free to jump in.
But like, how am I gonna get the code? Like, do I have to join AB group chat?
I'll do that. These codes actually change. Okay, they do actually change. Can you join by my ID number instead? If not, just message me and I can send you a code. Sorry, still a bit new to this. Didn't host. That's not it. Okay, we can try this. So this link here, I believe, works regardless of what I'm doing on Zoom. And we'll try that. Okay, if the code doesn't work for you on Monday, then send me a message on WeChat.
Yeah.
And I'll send you the invite. Okay. So stuff you missed. Do you want to go over it, or do you think you're okay?
I'm okay.
You're okay. All right. If you run into any problems while you're going through the homework, let me know. So just hit me up on WeChat, and I'll get to you when I can. Okay.
Yeah.
All right. Thank you so much for coming.
Okay. I'll see you around.
Yeah. I'll see you on Saturday. Goodbye.